In today's video, we will learn about buoyant forces. According to Archimedes and his principle, Archimedes stated that any object completely or partially submerged in a fluid is buoyed up by a force with magnitude equal to the weight of the fluid displaced by the object. Archimedes' principle helped us define buoyancy forces, which is a force when an object is placed in a fluid, and the fluid creates an upward force on the object. We write buoyancy force with a capital B, which is equal to the density of the fluid multiplied by the volume of the fluid displaced times the acceleration due to gravity. So we see when an object is completely submerged, we have the buoyancy force acting in a positive direction and the weight of the object acting in a negative direction. So if we have an object whose density is less than the density of the fluid, then the net force is positive and in the upward direction, causing the object to accelerate upwards. However, if the density of the object is greater than the density of the fluid, the net force is negative and in a downward direction, causing the object to accelerate downwards. And so a summary of our buoyancy forces is illustrated in our figure to the right. We see when there's a negative buoyancy, our object will sink. When there's a positive buoyancy, our object will rise to the surface. And if there's a neutral buoyancy, our object will stay suspended in the fluid that it is submerged in. If you look at our first example, it states that a wooden block of volume 5.24 times 10 to the negative fourth meters cubed floats in water, and a small steel object of mass is placed on top of the block. When 0.31 kilograms is placed on the block, the system is in equilibrium and the top of the wooden block is at the level of the water. And we're asked to find what is the density of the wood. So if we summarize the information we're given that the volume of the block equals 5.24 times 10 to the negative fourth meters cubed. And we see that the density of water is equal to 1,000 kilograms per meters cubed, and that the total mass of the system is equal to 0.310 kilograms. And so we can sum up our forces acting on the block. If we do so, we see that we have the buoyancy force acting in a positive upward direction and the total weight of the system acting in a downward direction. And it states that the system is in equilibrium, so our sum of our forces will be equal to 0. So we see that our buoyancy force will be equal to our total weight. And if we expand your equation, we have the density of water times gravity times the volume displaced of the fluid is equal to the density of the wood times gravity times the volume of the wood plus the force of gravity acting on the wood. And so we can cancel out our g's, and we're asked to solve for the density of wood. So if we get the density of wood by itself, we could rearrange our equation to see that the density of wood is equal to the density of water times the volume of the fluid displaced minus the mass of the object divided by the volume of the wood. So now we can plug in the values to solve for the density of our wood. We know that the density of water is 1,000 kilograms per meters cubed, and that the volume of the fluid was equal to 5.24 times 10 to the negative fourth meters cubed minus the mass of the system, which was 0.310 kilograms, divided by the volume of the wood that was displaced, which is also 5.24 times 10 to the negative fourth meters cubed. And so if we multiply this out, we see that the density of our wood will be equal to 408 kilograms per meter cubed. In our second example, it states that an empty barge 25 meters long and 4 meters wide floats with a water line at the mark of 1 meter below the surface. Gravel is added to the barge until it floats with a water line at 3.5 meters. What is the weight of the gravel, assuming that the barge is a rectangular solid? So we can summarize the information we're given. We're given that the length of the boat was 25 meters, and that the width of the boat was 4 meters wide, and that when the boat was empty, it was in equilibrium with the system, where the boat was displaced 1 meter below the water surface, and then after the weight was added, the boat was displaced 3.5 meters underneath the water. And so, if we sum up our forces acting on the boat, we'll have our buoyancy force acting in the upwards direction minus the weight of the barge when it's empty before the gravel was added is equal to 0. If we set our buoyancy force equal to the weight of the empty barge and expand our equation, see that buoyancy will be the density of water times gravity times the volume of the fluid displaced, which is the same as the area of the ship times the displaced height is equal to the density of the barge, which we'll say is the object, times gravity times its displaced volume, which is also the area of the barge times the change in the water line. And so we see that buoyancy and the weight of the empty ship are equal to each other. So when the ship is loaded with gravel, we can then sum up our forces again. So if we sum up our forces acting on the barge when it's loaded, we'll have the buoyancy force of the boat minus the weight of the loaded boat minus the weight of the empty boat equal to 0, since the system is in equilibrium. So if we rearrange the equation, we'll see that our buoyancy force will be equal to the weight of the barge plus the weight of the empty barge. So since we're trying to find the weight of the gravel, we can set the equation where the weight of the loaded barge is equal to our buoyancy force minus the weight of our empty barge. And this buoyancy force is a buoyancy force when the barge is loaded. So if we expand our equation, see that the buoyancy force of the loaded barge will be the density of water times gravity times the area times its new displaced water line minus the density of the object times gravity times the area of the barge times its original displaced water line. And we can say that the density of the object is equal to the density of the water. So if we factor out the density and the gravity, we'd get a new equation that states that the weight of the loaded barge with gravel is equal to the density of water times our gravity times the area of our barge times our change in our height of our water line, the final minus the initial height. So we can plug in the values we're given to solve for the weight of the gravel. So we know the density of water is 1,000 kilograms per meters cubed times acceleration due to gravity of 9.8 meters per second times the area of the barge, which is its length, times its width, times the final water line, which was 3.5 meters, minus the initial water line of 1.0 meters. And when we multiply our values together, we see that the weight of the barge with gravel will be equal to 2.45 times 10 to the 6th power newtons.